Hey class, I hope everyone is doing well and that you've had some good experiences as you've played with the Motors and Generators lab. What I want to look at today is kind of go through some of the fundamental concepts that you should have seen in today's lab. Okay, so first off, we had you look at a simulation where they shot a beam of electrons. Okay, so you have all of these little electrons and they're traveling this way, right, in this beam. And then the professor did it from behind, but I'm going to show it from the side, brought a magnet, a bar magnet, up towards the beam, and then there was an interaction, right? The beam bent. So what that's telling you is there was some kind of force, right? For some reason, this magnet caused a force to happen, right? So there's some force, and we want to know, where did that force come from, right? If this beam is going to bend, where's the force coming from that's bending the beam? Okay, and one way to think about this is we know that if you have moving electrons, that's kind of like it's kind of like a current. I mean, it is a current, but this is a beam in the air. Normally, we would have current in a wire. Okay. And so this little beam of electrons is going to create a magnetic field around it. And we looked at this and we investigated this the other day when we looked at magnetic fields that are generated around current-carrying wires, right? There's going to be a magnetic field around this thing that kind of like loops around it, right? You'd have this loop of magnetic field around here. And so if I brought a bar magnet in, north-south, that had its own magnetic field, right? The magnetic field of the bar magnet is going to interact with the magnetic field created by the beam, just like if I had two magnets and I brought them together, there'd be a force there, right? You get a force here if I brought two magnets next to each other. Well, I'm getting the same interaction here, where I have the magnetic field from the bar magnet interacting with the magnetic field that's generated around the beam of electrons. Right? Because moving electrons is a current, so that you get a magnetic field with a current, so you get an interaction and there's a force. Okay, so what we want to look at, and honestly, like, this is the fundamental principle. This is the fundamental principle that guides and governs motors, generators, all of that stuff is happening because there's a force acting between the field of the permanent magnet and the field of the moving electrons. Okay, so let's boil this down and kind of dig into this a little deeper. Okay, so what I want to draw is I'm going to draw a wire. Okay, and in my wire, let's say that it has electrons in it, and then let's say my electrons are moving this way. Okay, now this is weird, and it's a little silly that it is this way, but you're just going to have to deal with it. So if the physical electrons are actually moving this way, then the way that we talk about current conventionally is the current is directed to the left, right? So here's I, that's the current, and the current is directed it's pointed in the opposite way that the electrons are actually going. Now the reason why this is so here's a battery, right? You have the positive and negative terminals of a battery. And if I connected this with a wire to a light bulb, oh, that's the worst light bulb I've ever drawn. And then another wire, right? The people that set this up said, oh, well, the current goes from the positive end through the light bulb and then back in this way, right? That's the direction of the current. Well, they didn't know back then that it was actually the electrons moving and that the electrons were actually going this way. Okay? So they just picked that the current should move from positive to negative, and then they built everything around this idea, and then they found out, well, oops, the electrons are actually going the opposite way, but we're not going to change everything that we've already done, and we're just going to say that the current points in the direction that's opposite the way that the electrons are actually moving. I know that's ridiculous, but that's just the way that it is, and so we kind of have to live with it, okay? So in my simulation, so from here on out, I'm just going to talk about the current, but just know that the electrons are actually moving in the opposite direction that the current is, okay? So if I say that the current is going this way, to the left of the screen, so current going this way, what's the magnetic field going to look like? Generated by, so this is a review of what we looked at last time. Right, so if I stick using the right hand rule, the first way that we use it, if I stick my thumb in the direction, using my right hand, of the current, and I curl my fingers around this wire. So here, above the wire, my fingers are going to be pointing in, and below the wire, my fingers would be pointing out, right? If I curl around, they curl over the top and out the bottom, okay? So this is what's happening with the magnetic field generated by the wire, okay? And I'm just showing that so that we know and can recognize that yes, there is a magnetic field there, okay? And that magnetic field is going to interact. So here's a bar magnet, north, south. This bar magnet is also producing a magnetic field, and its magnetic field, we know from last time, looks like this, something like this, right? With the magnetic field pointing away from north, okay? And so what I'm telling you is that there's an interaction between the magnetic field of the bar magnet and the magnetic field generated by the wire, and it creates a force. So then what direction is that force in? And to figure that out, we're going to come down here, and we're going to use, this is the right-hand rule again, but this time we're looking at, this is like a second application of the right-hand rule, okay? So here's how it goes. So so here's a right hand, and in a two-dimensional space, this is as good as it's gonna get. But you want to stick your thumb in the direction of the current, okay? And then your index finger is going to point in the direction of so this is the external magnetic field. So this is the direction of the current. This is the direction of this field. And then the force is going to be the way that your middle finger is pointed if it was at a 90-degree angle to your pointer finger. So it's kind of like your pointer finger and your thumb, you can think of them as being in a plane, and your middle finger is 90 degrees to that plane pointing out, right? That's the direction of the force. So you have the current is your thumb, your pointer finger is the external field, and then your middle finger is going to be the direction of the force. So let's look at this, okay? So I'm just going to erase this for a second, and I'm going to erase all of that. Okay, so here we go. Here's the wire, here's the direction of the current, and we're going to say that there's some bar magnet creating a magnetic field that's this way. So I'm going to stick my thumb, stick your thumb in this direction, so there's your thumb. So it's like you're using your right hand, and then stick your finger, your index finger, is going to point, there's just your hand. That's the worst hand ever. In the direction of the field, okay? And then your middle finger here, it's like it's pointing into the screen, sticking out 90 degrees, like into the screen, right? So if you have your right hand and you hold it up, you've got your thumb to the left, your index finger pointing up, and your middle finger is pointing into the screen, and that's the direction of the force. So in this case, there'd be a force on this wire pushing into the screen. Okay? So let's look at, let's switch this up a little bit. What if Okay, here's my wire again. Here's my current. But this time, let's say that the magnetic field is pointing out of the screen. So here's an external magnetic field. So it's like I've got a bar magnet that's behind the screen with the north side facing out. Okay. So now what direction will the force be in? Okay, and so we got to think about this. And okay, so now stick your thumb in the direction of the current. Stick your index finger in the direction of the field. So it's like your index finger is here, it's pointing straight up. And then your middle finger is going to be pointing out like this. Like your middle finger is going to be pointing out this way. And then you have your other fingers that are tucked in. And that's your hand, right? With your index finger pointing up, your thumb pointing this way. And so your middle finger is pointing this way. So the force would be, it'd be like there's a force pushing the wire up. Okay? So that's how that works, right? Right-hand rule, I get a force because there's an interaction between the external field of the bar magnet and the field generated by the current carrying wire, okay? And everything to do with motors and generators is taking advantage of this force to do stuff, all right? So let's dig into this some more. Okay, so in the space of the motor, okay, so here you watch this video, and in class we would have built these, but it's like you've got a loop, and I'm going to draw this a little weird. So here's this thing, and then this is going to loop around, you know, and it loops, and then we send the wire back out, right? And normally we would have looped it like several more times, right? And then this could come over here, and here's a battery with a positive and a negative side, and this would come over here and touch this. Okay, and hold up. We got to imagine that there's a loop here, and that this part is free to spin. Okay, so think about this. Let's say that our loops right now are in the plane of the screen. And if this is metal, right, I can make a connection. The current is going to come this way, right? The current's going this way. It's going to come up. It's going to come into here. And it's going to travel around and out. Okay? But the point of this is that the current right here is moving this way. So that's I. And so now I almost have everything I need to get a force, right? So to get a force, I need a current, and then I need a magnetic field that's generated by something on the outside, and that's why they brought in like a little permanent magnet. So if you can kind of pretend that, let's say we set a little permanent magnet down here that's making a field that points. So if the south side was up, that field would point in. Okay. So now let's look at this and figure out, if this is my scenario, what direction is the force going to be on the wire? So if I stick my thumb in the direction of the current, right? So your thumb is this way, and your pointer finger is in the direction, so it's pointing down. So thumb, and then your middle finger is going to point in the direction of the force, that's this way. So on here, there's a force that's to the right. Okay, let me think about that, make sure I have it right. Yep. Make sure you're using your right hand for this all the time. Okay, it'd be like it's trying to squeeze that wire in. Now, is that going to be useful? In this orientation, no, not useful at all, right? That's not going to spin. I want this thing to spin. Okay, but imagine if I turned it just a little bit. So, right, if I rotated it this way just a little bit, so let me draw it again. So here's the loop. Here's this other loop. So what if I rotated it? So now my loop is here. So let's pretend that this is the loop. And there the little wire comes out. Again, if the current is still this way, and my magnetic field is still this way. And now my force is this way still, right? Because none of those things have changed. That's going to push this wire. It's going to push it to make it go over. Okay? And so every time this top wire is in this upwards position, it's going to feel a force pushing it this way. That's going to kick it around. Okay? And so this is what gives it the kick, right? And you saw in the video that the motor just starts spinning like crazy, right? And this is the reason why. This is what's going on. You've got a current, you've got an external field created by this magnet, and the reaction between the two fields there gives you a force that makes this thing kick around and spin, right? That's what a motor is. And that's all that's going on, okay? So we get a force, this thing spins, and we take advantage of this in all kinds of different ways, from making blenders to making vacuums, anything with a spinning part, a fan, right? It's all based off of this idea that that I can get an interaction between these fields to make force, okay? Then to kind of transition ourselves into looking at generators, we did this app where we played with Faraday's law, okay? And so in the simulation, you've got these loops of wires, right? And we recognize this thing, you can look at this and say, hey, look, that looks an awful lot like the electromagnet we built. And that's absolutely right. But now instead of connecting it to a power source, it's like we just connect it directly to the light bulb and then it runs back around and loops around, right? So then where's the power, right? How am I going to get this light bulb to light if there's no way to move the electrons, right? Normally I need a battery to move the electrons, but in this case, there is no battery to move the electrons. So what are we going to do? Well, if I have an external magnetic field created by a magnet, and if I have moving electrons, I can create a force. Okay, so we're gonna take advantage of this concept, but we're gonna do it in a sneaky way. Okay, because really, I just need the electrons to move relative to the field. So what if, look over here, in our motor example, the electrons are moving in the wire, and the magnet is stationary. What if I move the magnet? Right? And so that's what you guys did in this lab. You took the magnet and you moved the magnet back and forth. And you should have seen that when you were moving the magnet back and forth, the light bulb all of a sudden would light up. Okay? So it's like I'm creating like a ghost current by moving. I don't know if you can hear my children yelling in the background. But it's like I'm creating a ghost current by moving the magnet relative to the coils. Okay, and that movement, so it's like the magnet doesn't know if the electrons are moving or not, right? Imagine this thing is just full of electrons. Imagine there it is. It's just full of electrons, and if I move the magnet back and forth, to the magnet, it might look like the electrons are the things that are moving back and forth, right? So I just need that there to be like relative movement between the two, and you're gonna get a force, and the force is gonna push on the electrons, and in this case, that force pushes the electrons around inside the wire, and as the electrons wiggle around in the wires, that's technically a current, and the bulb can light. Now, does the bulb just stay on like as if you hooked it to a battery? No, right? The magnet has to be constantly moving back and forth for there to be a voltage, okay? And you would have seen that in this thing, and so Faraday's law is all based off of that, and you would have experimented a little bit by, if you change the number of loops, you can get a bigger voltage. If you have a bigger area, you can get greater voltages. That's another thing. Well, actually, you can't play around with that. The area in this one, I think you can change that in the next lab. But you can look at look if I have 2 loops versus 4 loops, right? How does that change things? And you could have seen differences in the voltages here. But really, Faraday's law is it's all about this relationship between fields, electrons, and force. Okay, that's what Faraday's law is talking about. That you can generate currents. Okay, so, and that's what a generator is, right? We're trying to generate a current. Okay, so then in the next lab, you would have looked at this, where here you have this weird spinny wheel, and as you turn the water on, it kicks the wheel and it makes the magnet spin, okay? And then if you look at the little compass needles, right, they kind of show you what's happening with the magnetic field. And as you can see here, right, so this one's really cool because you can see the electrons in the wire. And you notice that as this magnetic field is changing on the inside, it makes the little electrons, whoa, it makes the little electrons wiggle back and forth, okay? So notice that we never drive the electrons. They're never just going around and back and around and back, right? Nope. These electrons just wiggle back and forth, which means the electrons up here are wiggling back and forth. But that's all we need. That's, by the way, that's called an alternating current. So when the electrons are driven around and around and around and around, that's direct current. But if the electrons go back and forth, that's an alternating current. So something like this is going to give you an alternating current because there's a pattern, right, in the way that the magnetic field changes. Okay. So, taking a step back and looking at this all together, okay? I've got motors, I've got generators, okay? What a motor is I have a current, right? I create a current with a battery. And then I put that current in the presence of an external magnetic field, and that creates a force that I can then use to do things with. Blend up stuff, spin a fan, spin a vacuum belt, right? All of those types of cool things. That's what motors do. You provide the current in an external magnetic field, and that gives you force that you can do stuff with. That's a motor. A generator, on the other hand, it's like the opposite of this. With a generator, you provide the force, okay? You provide the force, still in some external magnetic field, right? So, right, this is always there and always the same. There's always this like weird external magnetic field, but you provide the force, and these two things make a current. And then I can use that current to power stuff or to charge a battery or to do something, right? So do you see how the mechanics here is exactly the same, but with a motor, I'm going one way down the list. And the generator, it's just the opposite, right? So motors start with a current, use an external magnetic field to get a force. Generators start with a force in an external field to generate a current, okay? I'm sure you've all seen those flashlights that have a little crank on them where you turn the crank like crazy and it charges a little battery that makes the flashlight go, right? You're the force. There's coils of wire and a magnetic field that gives you current, okay? In this example, the water is the force that spins this, that right? And the magnet there's your external magnetic field, and it gives you a current that then you can do stuff with, right? That's what this stuff is all about, right? This is the base mechanics of all of this, okay? And so you can see the similarities and differences in this chart. But it's all based off of this idea that we talked about here in the beginning, that moving electrons in an external magnetic field generates a force, okay? It all kind of goes back to that idea. So there's a lot going on in these topics. Please send us any questions that you have about this stuff. You can post questions in the discussion, or you can send us questions over email. But let us know what's going on. Let us know how you're doing, and good luck. This is the last of the electricity and magnetism stuff, and we are going to move on next time. Thanks, everybody. Bye.